Welcome back to the deep dive. For the past little while, we have been obsessed with fluids, but only in their most passive state, the world of hydrostatics.
Yes. Everything was calm, orderly, and at rest. Pressure just depended on depth. You had buoyant forces, a very peaceful world.
A peaceful world, but like you said, fundamentally incomplete. Today, we are turning the faucet on.
We are absolutely hitting the gas. We're plunging into the world that truly defines how our physical environment works. Hydrodynamics.
And this is where we introduce the one variable that creates all the complexity, all the mess, and all the fascination.
Time. The variable T. The moment fluids start moving, everything changes.
So the static pressure relationships we talked about, they're out the window. A dynamic, force-driven system takes over. Our mission for this deep dive is based entirely on the source material you provided.
And it's really the ultimate shortcut. We're going to guide you from, let's say, the fairy tale of ideal frictionless flow.
All the way to the messy, glorious, and literally million-dollar chaos of turbulence.
Exactly. If you want to understand how a massive cargo ship glides across the ocean, or how a jet engine works, or even just why a soccer ball curves when you kick it, you need the language of hydrodynamics.
Okay, let's unpack this. We have to begin with a core approach that physicists use to simplify what seems like infinite complexity. We start with the fluid element.
We have to. I mean, think about water flowing through a pipe. You can't possibly track the motion of every single water molecule. It's trillions upon trillions of them.
Computationally impossible.
Completely. So what we do is we zoom out a bit and we mentally isolate a tiny conceptual volume of the fluid. We can call it delta V or dV.
So just a little imaginary cube of water.
A little parcel of liquid. We assume it's uniform, and it's just moving along with the rest of the flow. We treat this little cube, this dV, as if it were a single object, a single point of mass.
And then we can apply the most fundamental law in all of classical physics to it.
Newton's second law. The foundational question becomes, which forces are acting on this tiny package of fluid as it rushes through the pipe or, say, over a wing?
And the entire field of hydrodynamics is built on answering that simple question.
It is. We answer it for that tiny element, and then we scale the answer up to describe the whole flow.
All right, so let's identify the forces. The first one is familiar, the standard one everyone knows.
The weight force, Fg.
Gravity.
Just gravity. It's straightforward. It's simply the density of the fluid, ρ, times gravity, g, times the volume of our little element. It always pulls it straight down.
And in a lot of cases, like a horizontal pipe, we can kind of ignore it for a bit.
We can, yeah. We set it aside temporarily, but it's always there, waiting to become important as soon as the fluid changes altitude.
But the real driver of the dynamics, the force that makes the system move horizontally and causes all the interesting pressure changes, that's the pressure force, Fp.
This is the critical concept we have to get right. Our little fluid element is surrounded by pressure on all sides.
Right.
Now, if the pressure pushing on the front face of our cube is exactly the same as the pressure pushing on the back face,
They just cancel out.
they cancel. The net force is zero. Nothing happens. No movement is generated.
So a dynamic pressure force only exists if the pressure is different on either side of the element.
Yes, you need a pressure gradient. That's the key. If the pressure on one side, P1, is higher than the pressure on the other side, P2, that difference creates a net force.
And the math in the sources shows this force is proportional to the negative pressure gradient. Why is that negative sign so important right now?
Because it tells you everything about the direction of flow. The negative sign means the force always acts from high pressure to low pressure. The fluid is literally driven away from where it's being squeezed and pushed toward the area where there's less resistance.
Like squeezing toothpaste from a tube.
The perfect analogy. The high pressure you create at the bottom of the tube drives the paste toward the low pressure opening. That's the dynamic pressure force in action.
So this is a theme we'll keep coming back to. If a fluid is speeding up, it must be moving into a region of lower pressure.
Absolutely.
Yeah.
Now, there is a third force we have to acknowledge, even if we're going to set it aside for a moment. For real fluids, there's the friction force.
Or the viscous force, Fr.
Right. That's the internal resistance. It's what makes honey different from air. We'll get back to it, but for now, we'll live in the ideal frictionless world.
Okay, so if we can track these forces, gravity, pressure, and eventually friction, what's the ultimate goal here?
The goal is to find the flow field.
The flow field, what does that mean?
It means knowing the velocity vector, which we call u, at every single location in space and at every single moment in time. If we know u of r and t, we've solved the entire system. We know everything.
But solving for that in its full, time-dependent, three-dimensional glory sounds monumental.
It is. So, like all good physicists, we start with a powerful simplification. We assume stationary flow.
And stationary flow does not mean the water is sitting still.
No, absolutely not. The water's moving. It means the overall pattern of the flow doesn't change over time. The picture of the streamlines is fixed.
What's a good analogy for that?
Think of a fast river flowing past a big concrete bridge pillar. The water molecules themselves are flying downstream, right? But that little whirlpool, the eddy that forms right behind the pillar where leaves and debris get stuck,
It's always in the same spot.
always in the exact same spot.
Yeah.
It's a dynamic process, but it's reached a static, unchanging structure. So mathematically, the velocity vector u doesn't explicitly depend on time, on t.
And that assumption is what lets us start talking about acceleration in a manageable way.
Exactly. But this is where we have to be really careful, because this is probably the single trickiest concept in all of hydrodynamics.
Understanding total acceleration.
Yes, we have to distinguish between the acceleration you'd see at a fixed location and the acceleration a moving particle actually feels. They are not the same thing.
Okay, let's start with the easy one. If I stand at a single fixed spot in the flow, say right at the mouth of a faucet, and you suddenly turn the handle,
The speed you measure at that fixed point changes. The rate of that change is what we call local acceleration. Mathematically, it's the partial derivative of us with respect to t.
and for the stationary flow we just talked about, where the pattern never changes.
That local acceleration is 0, which is a huge help.
And now for the tricky part. Let's imagine flow in a pipe that steadily gets narrower, a funnel shape, and we follow a single drop of water.
Okay, if the flow is stationary and I stand at a fixed point inside that narrow section, the speed I measure is constant. It's always fast there.
So local acceleration is 0.
It's 0. But think about that drop of water. As it moves from the wide section into the narrow one, it must speed up.
Of course, it has to.
So it is accelerating, even though the overall flow pattern is totally fixed in time.
So it's accelerating just because it's changing its location.
Precisely. It's moving into a region where the flow velocity is spatially higher. This is the convective acceleration.
The acceleration it experiences because it's being swept or convected into a different velocity region.
Think of cars merging onto a highway. The highway itself, the flow pattern, is stable and fast. If you're a single car coming from the slow on-ramp and you merge onto that fast highway, you have to accelerate.
Right. I'm accelerating because of where I'm going, not because someone changed the speed limit over time.
That distinction is profound. A fluid element can accelerate even when the whole system looks completely steady. And this convective term is the mathematically complex one. It's the nonlinear term.
Written as that kind of scary-looking del u dot del u.
Which really just means that the acceleration depends on how fast you're already going, multiplied by how quickly the velocity field is changing around you.
But the physical takeaway is what's important. The fluid speeds up because the pipe narrows.
And when we talk about the total acceleration, the real acceleration that our fluid particle feels, we have to add both of these together.
The local term, in case someone's turning the faucet, and the convective term, in case the pipe is narrowing.
And now that we have that total acceleration, we are finally ready to write down the foundational equation for frictionless fluids, Euler's equation.
Back to Newton, F equals ma.
We apply it to our little fluid element, dv.
Mm-hmm.
On the left-hand side, we have mass times total acceleration. So that's density, rho, times the volume, dv, times that whole acceleration term we just built.
And on the right-hand side, for an ideal fluid, we have the sum of the forces.
Which for now are just gravity and the pressure force.
And when you put it all together and divide out the volume element.
You get the famous Euler equation from 1755. It's the elegant, perfect statement of momentum conservation for an ideal fluid.
The left side is how the fluid's motion is changing, its inertia. The right side is what's making it change, gravity and pressure differences.
It's Newton's second law for a continuous medium. And it's the, let's call it the simplified little brother, the much bigger, more complex Navier-Stokes equations we'll see later.
Okay, so Euler's equation handles momentum, but that's only half the story. There's another absolute rule we have to enforce.
The mass must be conserved.
Matter can't just appear or disappear.
Exactly. Whatever flows into any small volume must equal what flows out, unless the material is, compressing or decompressing inside that volume.
And this gives us the continuity equation.
We get this by doing a careful mass balance on our fluid element. We calculate the rate of mass flowing in through all the faces versus the rate of mass flowing out. Any difference means the mass inside must be changing.
And this in versus outflow is measured by the spatial derivatives of the velocity.
Right, and the combined measure of that is called the divergence of the velocity field. Conceptually, the divergence just tells you if the velocity field is spreading apart, like from a source, or converging together, like into a sink.
And the continuity equation links the change in density over time to this divergence.
The physics of it is crucial. If the divergence is positive, meaning the velocity lines are spreading out, the fluid has to be thinning out to conserve mass.
So its density has to drop.
Its density, ρ, must decrease over time. This is what happens with a compressible fluid, like air.
But most of the time in daily life and engineering, we're dealing with a huge simplification.
We're dealing with water.
An incompressible fluid.
Yes, for which the density is basically constant no matter what. So the change in density over time is 0.
And if that's 0, the math immediately tells us that the divergence must also be 0.
Which is a really powerful result for flow in a pipe. It means there are no sources or sinks. The volume flow rate has to be constant everywhere.
And this simplifies down to that incredibly useful rule. Area times velocity is constant. A1U1 equals A2U2.
This is why the garden hose effect works so dramatically. If you put your thumb over the end of the hose and you cut the area down by 90%.
The velocity has to increase by a factor of 10 to keep the volume flow the same.
It's not magic. It's just the law of continuity.
Okay, so continuity forces the velocity to change in a narrowing pipe. Now we have to go back to Euler's equation and see what that does to the pressure.
And this is where everyone's intuition goes completely wrong.
My gut tells me that if water is moving really fast, the pressure must be high. A jet of water feels like high pressure when it hits you.
Yes, that feeling is the dynamic pressure converting back to static pressure when it hits your hand and stops.
Yeah.
But inside the moving flow itself, the opposite is true. And this brings us to Bernoulli's equation.
To get there, we start with Euler's equation for stationary flow, and we ignore gravity and friction for a moment.
We're left with a balance between the convective acceleration and the pressure gradient. When you integrate that relationship along a streamline, the math cleans up beautifully.
And you're left with one of the most famous equations in physics.
P plus 1/2 rho u squared equals a constant.
This equation is just a conceptual masterpiece. It forces you to see a fundamental trade-off in the flow.
The sum of the static pressure, what we call the dynamic pressure, that 1/2 rho u squared term, has to remain constant.
It's energy conservation.
That's all it is. It's the work-energy theorem for fluids. If the fluid gains kinetic energy, meaning that dynamic pressure term goes up because the velocity u is high,
It has to pay for that speed by reducing its static pressure.
which leads to the crucial insight. Where velocity is high, the static pressure must be low. This is the Bernoulli effect.
Let's visualize this with the Venturi effect from the sources. You have water flowing through a pipe that narrows in the middle and then widens out again.
Continuity forces the fluid to accelerate like crazy in that narrow throat.
And if you attach vertical pressure measuring tubes along the pipe, what do you see?
The evidence is undeniable. In the wide sections, where the flow is slow, the static pressure is high, and the water level in the tubes is high. But in that narrow high-speed section, the water level in the pressure tube sinks. It drops dramatically.
It traded its pressure energy for kinetic energy.
Exactly. And of course, for the full picture, we can add the potential energy term back in, rho OGH, to account for any changes in height.
Giving us the complete Bernoulli equation. Pressure energy plus kinetic energy plus potential energy is constant along a streamline.
And this one principle, even though it's for an ideal fluid, lets us calculate an incredible range of things, from water flowing out of a tank to dynamics in hydroelectric plants.
The fact that it's so counterintuitive is responsible for some really surprising phenomena.
Oh, absolutely. Let's start with what's often called the hydrodynamic paradoxon. It's a classic demo.
Okay.
Imagine you hold 2 sheets of paper, or 2 light plates parallel to each other, maybe a centimeter apart,
Yeah.
and you blow a strong, fast stream of air right between them.
My intuition says the air pressure inside will build up and push the plates apart, like inflating a little balloon between them.
That's what everyone thinks. But Bernoulli says the opposite has to happen. That fast-moving air between the plates causes the static pressure P to drop below the surrounding atmospheric pressure.
So the normal, slow-moving air outside the plates is now pushing in harder than the fast-moving air inside is pushing out.
And the result is a net suction force that pulls the plates together. It's a profound demonstration that high speed fundamentally means low static pressure within the flow.
You can actually make things hover with this effect.
You can. You can use the suction to lift a second disk against gravity. The entire lift is paid for by that kinetic energy term, 1/2 rho u squared.
And this paradox is scaled up to a monumental level in the most important application of all this.
Wing lift. Aerodynamics.
How airplanes fly.
Exactly. The wing, or airfoil, is designed to be asymmetric. It's curved on top and flatter on the bottom. This forces the air that goes over the top surface to travel a longer distance than the air that goes underneath.
And if it has to travel a longer distance in the same amount of time?
Continuity dictates it has to move faster. So you get a higher velocity u1 over the top surface.
And higher velocity means?
Lower static pressure. Meanwhile, the slower flow underneath has a higher pressure.
And that pressure difference, multiplied by the huge area of the wing, is what generates the lift force that gets the plane off the ground.
It is a massive controlled application of the Bernoulli effect. Now, we should add a little clarification. Real aerodynamic lift is a bit more complex. It involves the wing's angle of attack and something called circulation.
But the high-speed, low-pressure trade-off is still the central mechanism.
It's the fundamental reason it works.
Okay, that wraps up our time in the, as you called it, fairy tale world of ideal fluids. No friction.
Yes, a beautiful, clean world. But now we have to get real. We have to introduce the force that complicates everything.
Viscosity.
Viscosity. The measure of a fluid's internal friction. It's resistance to flowing. It's the difference between pouring water and pouring honey.
And the key concept here is something called the no-slip condition.
Right. Imagine fluid between two plates. If we start moving the top plate, the layer of fluid right next to that plate moves at the exact same speed as the plate. It sticks to the surface.
And the layer sticking to the bottom, stationary plate, has 0 speed.
This creates a velocity gradient across the channel. And to keep the faster layers sliding over the slower layers, you have to apply constant force to overcome that internal friction.
And the sources show that this force is proportional to the area of the layers and that speed gradient. The constant of proportionality is the viscosity, eta.
And the values can be wildly different. If we call water's viscosity 1, then glycerin, which is common lab fluid, is about 1,480 times more viscous. It takes almost 1,500 times more force to get it to flow in the same way.
And here's a fascinating detail. If you warm up a liquid, like honey, its viscosity drops. It gets easier to pour.
It does, because the molecules can slide past each other more easily. But if you warm up a gas, like air, its viscosity increases.
That is completely backwards. Why?
Because gas viscosity is all about molecules colliding and transferring momentum between layers. Heat them up, they move faster, they collide more, and the friction between layers actually goes up. It's one of those amazing differences between states of matter.
Okay, so how does this friction translate into a net force on our little fluid element? This is subtle.
It is subtle. Because if the velocity profile is perfectly linear, a straight line from 0 at the bottom to max at the top,
Yeah.
then the friction force pulling the element back from the slower layer below is perfectly canceled out by the friction force pulling it forward from the faster layer above.
So there's no net force, even with friction.
Not if the profile is linear. A net friction force only arises when the velocity profile is curved.
Ah, so the gradient itself has to be changing.
Precisely. The forces only fail to balance if the profile is curved. So we're looking for the rate of change of velocity.
Which in calculus is the second derivative.
It's the curvature of the flow profile that generates the net drag force on the element. And since flow is three-dimensional, we have to sum up all the second derivatives in all directions.
Which sounds like a mathematical nightmare.
It would be, but thankfully there's an elegant shorthand for that operation. The Laplace operator, represented by a triangle, delta. This lets us write the entire viscous drag force in one clean term. Viscosity, eta, times the Laplacian of the velocity vector, times the volume. That one term contains all the internal friction.
So we have finally assembled our full inventory. We have inertia, gravity, pressure, and now friction.
It's time to put it all together, to assemble the master equation of classical fluid dynamics.
The Navier-Stokes equations.
We go back one last time to Newton's law. Mass times total acceleration equals the sum of all forces.
We're taking the ideal fluid equation, Euler's equation, and we're just adding the new viscous drag term to the right-hand side.
And that's it. The left side is still the total inertia. The right side is now the full menu of forces. Gravity, the pressure gradient, and now the viscous term.
That equation looks incredibly intimidating on paper, but the key is to translate it into simple physical actions. The source material had a brilliant analogy for this.
The crowd analogies, it's perfect. Let's walk through it. Imagine you were a single person, our fluid element, in a massive, dense crowd pushing down a street.
Okay, I'm in the crowd. The left side of the equation is my acceleration.
Right, so term one, the local acceleration. This is your speed changing because, say, a traffic light way up ahead turns green and everyone just starts moving faster. The change happens at your location just because time is passing.
Term two, the convective acceleration, the tricky one.
This is you speeding up because the street narrows. The crowd as a whole hasn't changed its pace, but you've been swept into a bottleneck where everyone is forced to run faster. You accelerate just by changing your position.
Okay, that's the inertia. Now for the forces on the right that cause it.
Term three, gravity. That's easy. The street starts going downhill, gravity pulls you along.
Term four, the pressure gradient.
This is the pushing. You feel people pressing harder on your back than on your front. You naturally move forward into the open space where the pressure is lower.
And finally, term five, the new one, viscous friction.
This is the internal drag. If the people right next to you are running faster, they sort of drag you along with them. If they're moving slower, they hold you back. It's the friction caused by speed differences with your immediate neighbors.
And that's it. That is the complete Navier-Stokes equation. It describes basically every flow you can see.
From a ripple on a pond to the largest atmospheric currents on a planet, its universality is what makes it so important. It governs airflow over a race car, blood in your veins, the weather.
But it's also famous for its complexity.
Infamously complex. Finding a complete, general mathematical solution that proves smooth solutions always exist, that remains one of the 7 Open Millennium Prize problems.
There's a $1 million prize for solving it.
There is. The complexity comes from that nonlinear convective term. That's the mathematical seed of chaos and turbulence, and it's why this problem has stumped mathematicians for over a century. It's truly the biggest unsolved mystery in classical physics.
Fortunately, we don't always have to solve the full chaotic version. We can simplify it for specific, very important cases.
Yes, we can solve for flows that are laminar. That means layered, orderly flow.
Like flow between two fixed walls driven by a pressure drop.
In that steady-state case, the acceleration is 0, and we can ignore gravity. So you have a perfect balance. The driving pressure force must exactly equal the resisting viscous friction force.
And when you solve that differential equation
And apply the no-slip condition, 0 velocity, right at the walls, you find that the velocity profile is a perfect parabola. Smooth, predictable, fastest in the middle.
a more practical version of this is flow in a circular pipe. This is the domain of the Hagen-Poiseuille law.
The physics is identical. Pressure drives, viscosity resists. We just solve the equations in cylindrical coordinates. The result is still a parabolic profile, just rotated into a 3D shape, a paraboloid.
But the critical step for any real application is calculating the total volume flow. How much stuff is actually getting through the pipe per second?
To get that, you have to integrate that parabolic velocity profile over the entire circular cross-section of the pipe.
And when you do that math, something astonishing and crucial is revealed.
The Hagen-Poiseuille law. It shows that the volume flow rate is proportional to the radius of the pipe, r raised to the 4th power.
I cannot overstate how dramatic this r to the 4th dependence is. This might be the single most important practical takeaway from this entire deep dive.
Let's really hammer this home. If you double the radius of a pipe, you don't double the flow. You don't even quadruple it. You increase the flow by 2 to the power of 4.
16 times.
16 times more flow. Conversely, think about arteriosclerosis, plaque narrowing an artery. If you reduce the effective radius by just half,
The flow rate drops to 1/16 of its original capacity.
it's a catastrophic reduction.
Yeah.
A tiny change in geometry has a massive effect on transport capacity. This governs your plumbing, your hydraulics, and your circulatory system. That r to the 4th law is everywhere.
That beautiful, orderly world of laminar flow is mathematically nice, but it only lasts so long.
Right. As you increase the flow speed, that orderly layering just breaks down completely. It leads to wild, chaotic flow with eddies forming and dissipating constantly. Turbulence. And the question is, what single factor determines when the flow goes from ordered to chaos?
The answer comes from Osborne Reynolds, who found a brilliant way to distill the entire Navier-Stokes equation down to a single dimensionless number.
The Reynolds number, ρ. It's defined as density times velocity times a characteristic length, all divided by viscosity.
But the physical meaning is what's really important. It's a ratio of two competing forces in the fluid.
Exactly. It's the ratio of inertial forces, the fluid's momentum, which wants to keep going and create instability, to the viscous forces, the internal friction, which tries to damp out disturbances and calm everything down.
It's a battle between inertia and viscosity.
It is. If the Reynolds number is low, viscosity wins. The flow is thick, slow, and stable. Any disturbance gets smoothed out immediately. Think of honey dripping.
And if the Reynolds number is high,
Inertia wins. The fluid's momentum is so high, the viscosity can't contain it. Any tiny disturbance gets amplified and explodes into full-blown chaotic turbulence.
and this number is also why wind tunnels work.
Yes, the law of similarity. If you test a small-scale model of a plane, but you do it in conditions where the Reynolds number is the same as the full-size plane will experience.
The physics of the flow, the drag, the lift, the turbulence, it will all be identical. The flow only cares about that ratio.
Now, turbulence means vortices, swirls. In our ideal frictionless world, vortices can't just be created out of nowhere.
But in the real world,
Friction generates vortices, especially when flow hits an obstacle. And a beautiful example of this is the Kármán vortex street.
what's that?
When flow goes past a cylinder at a certain Reynolds number, vortices peel off the back, alternating for the top, then the bottom, then the top again. It creates this continuous, oscillating trail of swirls downstream.
A street of vortices.
A street of vortices. You can sometimes see these in satellite photos, in cloud patterns forming behind large volcanic islands. The mountain acts as the cylinder in the airflow.
And the ultimate vortex is on Jupiter.
The Great Red Spot, a gigantic, centuries-old turbulent storm. It's what happens when inertia wins on a planetary scale.
Okay, let's wrap this all up with one last effect that brings everything together, something every sports fan knows.
The Magnus effect.
The banana shot in soccer.
Exactly. This applies to any spinning object moving through a fluid. The key is that friction causes the surface of the ball to drag the air along with it.
So for a ball with topspin moving left to right, on the top surface, the rotation is moving in the same direction as the oncoming air.
Which creates a region of even faster total flow on top,
And on the bottom, the rotation is moving against the airflow.
creating a region of slower total flow underneath.
Now we just applied Bernoulli's principle one last time. Faster flow on top means...
Lower pressure. Slower flow on the bottom means higher pressure.
And that pressure difference creates a net force.
A powerful force that pushes the ball from the high-pressure side to the low-pressure side. With topspin, that's a downward force, making the ball dip sharply. With side spin, it makes it curve sideways.
So that curve is the physical evidence of Bernoulli's principle, triggered by the friction of a spinning object. It's a perfect combination of everything we've discussed. That was quite a journey. We started with a single, tiny fluid element, and we ended with planetary storms and curving soccer balls.
We moved from the ideal, frictionless world of Euler to the messy, complex reality of viscosity and the Navier-Stokes equations.
And we established those two crucial trade-offs. The first is the balance between pressure and speed from Bernoulli. You pay with pressure to get speed.
And the second is the battle inside the fluid itself, captured by the Reynolds number. The battle between inertia, which drives chaos, and viscosity, which tries to enforce order.
And the practical takeaway, that incredible R to the fourth law for pipe flow. A small change in diameter means a massive change in capacity.
Those are the key ideas to hold on to.
So, if you leave this deep dive with one final thought to mull over, consider the philosophical weight of the Navier-Stokes equations. This set of 5 terms describes the flight of a plane, the turbulence in a river, and the chaotic storms on Jupiter.
We know the exact equation, we can write it down, and yet solving it completely is a million-dollar problem that has eluded the greatest minds for a century.
So think about the systems in your own daily life. The way syrup pours, the invisible air currents in a room. Do they contain a level of complex, maybe even unsolvable physics that's equivalent to predicting the entire atmosphere?
And every time you see a fluid move, ask yourself which force is winning that unseen battle in that exact moment. Is it inertia driving toward chaos? Or is it viscosity trying to pull it back into peaceful, orderly layers? That constant dynamic battle that is the reality of hydrodynamics.